Okay, good afternoon, everyone. My name is Mohammed Aborg. This is my partner, Ahmed Abdal. The name of our project is Aquapore, and our consultant is Professor Eric Cruzet. Firstly, I'll go through the outline of our presentation. And part one is I'll introduce you to our design, to the science behind capacitive deionization, how it works, and what role it plays in desalination technology. Part two, I'll go through the specifics of our engineering design and analyze the design criteria that we went through. Part three, we'll go through the experiments that we carried out and the results as well. And part four, we'll go through the conclusions and the improvements that could be implemented to improve our project. So, part one, capacitive deionization. It's a desalination method. It's to remove salt ions from water solutions. The motivations for it is obviously the availability of clean water is really important in our generation, and it'll only become more important in the generations upcoming. And another problem with the with the availability of clean water is that groundwater extraction is actually causing the water sources to become more saline, and the concentration of salt is actually increasing in our sources. And so the idea of capacitive deionization, it's pretty much using electric fields to remove salt ions from a water solution and storing them in the electrodes. The idea is actually not that complex. It's been around for a long time. It's only recently gained a lot of momentum due to the developments in nanomaterials and nanotechnology. And so to go through like the basic concepts is, so you have parallel electrodes, which are very porous, and a bias is applied across these electrodes, which creates an electric field which acts on the ions. These ions are taken out of the water solution and stored into the electrodes. So in an actual commercial unit, you'll have many of these stacks. The current technologies used for desalination are reverse osmosis. And reverse osmosis, I'll go into detail more about it, but it's a very energy-consuming process. And as I said, it makes it more attractive because it's robust, cost-effective, it's energy efficient for low ion concentrations. And unlike many of the other desalination technologies, it's removing the minor component, the minor constituent. For example, reverse osmosis, you're removing the water out of the salt, whereas in CDI, you're removing the small component, which is the salt ions. So it's based on voltage difference between electrodes. You get an electric double layer. Brackish water means just the concentration is 10 grams per liter. It's very common in groundwater. It's very common in wells. Salt water is much higher than 10 grams per liter. It's around 20 grams. But the main application is for this brackish water. So yeah, most of the electrodes made now in the CDI component are porous carbon electrodes, obviously due to their conductivity and surface area. So so the stages in capacitive deionization are purification, regeneration, and flushing. It's more clear in the diagram in the next slide, but pretty much you get ion electrosorption, and the ions in water are mainly monovalent, divalent, like sodium, chlorine, calcium. So the ion capacity of it depends on the electrical capacity of the double layer. You know, the thicker the double layer, the more ions you're going to extract from the solution. So this is just a basic diagram of what it looks like. You've got your current collector, which is just usually a metal wire. The porous carbon electrode, the main component in the capacitive deionization. And you've got your cation and anion exchange membranes. The purpose of these membranes is so that it'll become more clear in the animation, but you don't want the oppositely charged electrons to go into the electrodes, the oppositely charged ions to go into the electrodes in the regeneration stage. It'll become more clear in the next one. So, so you've got your saline water, your saltwater solution, and coming in, and your output is the deionized water. So your salt solution comes in, your ions get trapped in the electrode. You end up with deionized water. But of course, after a while, your electrodes become saturated. The concentration of salt ions becomes too much. So then the next stage, as I said, is the regeneration, where you switch the charge, you switch the polarity, the voltage, and now you're pushing it out. See, however, the obsolete charged ions, they don't go in because of the membranes that exist there. That's why the membrane is an important function of it. And you end up flushing out the bad water, the salt water. And so it's cycles of deionized water and salt water. And then you just go back to you repeat the same process. So as I said, the main component is the electrical double layer, and obviously the electrical properties of your material are very important, but also the surface area as well. A thicker electrical double layer will allow you to extract more ions. And also, the higher the surface area, the more electrical double layers you'll be able to form. So the competing technologies are distillation, reverse osmosis, electrodialysis. Main one, though, is reverse osmosis. Reverse osmosis is pretty much high pressure of the high pressure acting on the saltwater solution pumped through a membrane. It's a very energy-consuming process. You've got really high pressure acting on it. This is just a diagram of what it looks like. It's being pumped into it. And again, you're moving the main component. You're moving the water. CDI extracts ions. It's energy efficient below 10 grams per liter, and it's a pure physical process, which is really important for the lifetime of your material. There's no chemical reactions occurring. It's just based on electrostatic forces, which is a physical process, usually means a longer lifetime. And this is just a graph showing the energy consumption. Reverse osmosis is just removing water. It's not relative to the saltwater concentration, so it's flat. That's the RO. But MCDI, the capacitive deionization, after around 30 millimoles, becomes not as efficient.
For our engineering design, we decided to coat our material on a nickel foam. We decided on nickel foam because it's conductive, it has a high surface area, it's stable in water, and it's flexible, and also it's not very expensive. First, we decided that these are the main components of our design. We decided to coat using CNT as a scaffold due to its high surface area and its high mechanical properties, and also its porosity. And to make our setup more efficient, we decided to use polypyrrole as a conductive polymer. And then we needed to, since we are spray coating our device, we needed a binder, and we decided to use Nafion as a binder. This is the steps we took to functionalize our CNT. The process for functionalizing CNC is a little more involved, but the main steps are pretty much similar. So you add an acid, and once you add an acid, then you do a reflux for around 24 hours to 48 hours, depending on how much functionalization you want to do. And then you filter your solution, and you take your filtrate, you add your polymer to it. You take your filtrate, you add your polymer to it, and you add an initiator, and you let it stir it for around 24 hours, and then you take your filtrate again, and once you have your filtrate, you dry it into a powder. This powder we then is shown in the image. It's not very clear here. Okay, this powder we then we solubilize it in, for the CNT one, we solubilized in isopropanol. For the CNC one, we solubilized in DMSO. Once we do that, we add the Nafion for the binder, and then we spray coated it into our film, and you get a film which looks pretty much like this. This is a cost breakdown of our products. Since we use very little of the products of the materials, so the cost was not that high. But if we are going to be using this for a commercial product, the differences would obviously start to increase. We took a commercial product and we tested it. We found out how much it costs. The commercial product they use at the moment is made up of graphene with porous carbon, with carbon black on it, and it costs around $3 per gram, while ours costs around $6.7 to $6.19 per gram. We actually had a couple more films that we tested, but they were made out of stainless steel, and they had platinum and cobalt in them, which increased the prices a lot higher than this. So we decided to settle on CNT and CNC films, since they're more cost effective. These were some of the customer requirements that we had. We wanted to test, we had conductivity. The higher the conductivity, the better your product. Surface area, obviously, for the porosity. The more surface area, the more electric double layers you can form, the better your product. And since you don't want to be replacing your electrode every day or something, so you need a stability stability of it for your product. So we decided to test around 500 cycles. And uniformity, uniformity of your product is also important. To test all of these, we decided to use a 4-point probe for the conductivity, a BAT for the surface area, and cyclic voltammetry for the stability with SEM images for uniformity. And then we added our own test for the salt absorption using a 2-electrode setup, which I'll go through in the next couple of slides. BAT isotherm is a standard process for testing porosity and surface area. It measures the specific surface area based on how much gas the molecule can absorb on top of it. This allows you to determine pore volume, specific surface area, and porosity. While the 2-electrode setup we devised was you have 2 electrodes of the same material, and you apply a voltage between them, and then you test the conductivity, how much the conductivity changes before and after your test. These were some of our porosity results for our films. While the commercial product had a lot more porosity than ours, the main one we tested against, ours were actually higher than our customer requirements, which are around 0.2. We got 0.3 for our CNT ones and 0.65 for our CNC ones. These are some of the images. This is the nickel foam, and the stuff you can see through the nickel foam, that's where the CNT and the polypyrrole have been deposited. I have a next image over there. Yes, and that's the CNT polypyrrole on your left, and the CNC polypyrrole on your left, and the CNT polypyrrole on your right. You can see all the polypyrrole molecules, and you can see the CNT and the CNC with the polypyrroles connected to them. When we took these images, the CNT and the CNC we functionalized. We had a much higher functionalization for CNT than CNC, since the process to functionalize CNC is a lot more involved and a lot harder. And we weren't actually we've never used it before, so our results were not as high as we expected. We only got around 20 to 30% functionalization, while for CNT we got like 40 to 50% around functionalized. This can be increased further to around 70 to 80%. I've read actually a couple of papers that have actually such high functionalization. Obviously, the higher your functionalization, the better your electrodes would be. This is the 2-electrode setup. It's very basic. You have just the 2 electrodes. You connect them to around 0.8 volt. And we use 0.8 volt because the water itself starts breaking down at around 1.2, 1.4 volt. And after some stability tests, we found that our electrode stays more stable at 0.8 volt. At 0.8 volt, if we increase to around 1 volt, it starts breaking down much faster. So we did all our tests around 0.8 volts. This is our test for the absorption. We did tests over different initial concentrations of NaCl. Since we're doing this test mostly for brackish water, that's around 2 to 10 grams per liter, so we only tested in that range. So as you can see, the higher the initial concentration, the more the more absorption you can do. And the green line is a commercial product. The red line is the CNC product, and the blue line is our CNT product. As you can see, the CNT actually absorbs around 10 to 14% of the ions, while the commercial product only absorbs 2 to 3%, and the CNC is around 3 to 5%. The reason we think that we have a slope like this is a mass transfer limited process for absorption. So the ions have to travel from your solution to your electrodes to be absorbed. And since our voltage is only 0.8, only the ions that are close to the electrodes actually are getting absorbed. So when you have a higher concentration, you have a lot of ions around your electrode. So you absorb a lot more ions than if your concentration is low and there's not a lot of ions. So you only absorb a little bit of the electrons, of the ions, I mean. And this is desorption. When we tested the desorption, we only tested for around 3 minutes. For around 3 minutes, and as you can see, since at higher concentrations you're absorbing more, you can see that you release a lot more too at the higher concentrations. And if we wanted to make this more efficient, we probably have to do. We found that it will take the test to actually, if you want to remove all the ions, would take at least like 30 to 40 minutes. So that would have taken way too long. We didn't actually have the time to do all that, so we did our tests in around 3 minutes only.
So this is the criteria that we used to analyze whether our project was successful or not. And these are basically pretty much the customer requirements. And the first one, conductivity, we didn't meet. We got a much lower reading. We got 0.5 Siemens per centimeter, which is a lot lower. And the reason we believe that happened is because the degree of functionalization was actually really low for CNC and wasn't that high for CNT either. I think for CNC it was around 20%, which is not what you want, because the polypyrrole is what's bringing the conductivity, and if it's not functionalizing, it's not coating the CNC particles, which if, I'll just go back to the, So like from the image from the CNC and the polypyrrole, you can see that there's not many polymer particles aggregating on the CNC fibers. The CNC are the long-stranded ones. The polymer is kind of aggregating by itself. It's coming together. It's not taking advantage of the CNC substrate. Whereas CNT, we got a good degree of polymerization. You can kind of, I don't know if it's clear, but you can kind of see the particles coating the carbon fibers. So that was the main reason why we believed our conductivity was much lower than what we wanted. However, surface area was really high. We got 792 meters squared per gram, and that's probably due to both CNC and especially CNT are really high surface area, and incorporated into the nickel mesh or the nickel foam results in really good surface area results. And the stability, those were done through CV. We did around 500 cycles. We didn't notice any significant changes. However, CNC did not have good stability. And the reason for that was because it was just degrading in the solution. Uniformity was also pretty good, and this was analyzed through the SEM images. Achieved the standard deviation of 0.8, and our goal cost was to stay below $10 per gram, and that was also successful as well. However, the commercial cost is usually around $3 per gram, and ours was, I believe, around $6 per gram. It was still successful, low scale. We could also improve the cost as well we didn't make we weren't really efficient with the ingredients that we used. There was a lot of waste products after we created it, so that would also be another improvement, to be more efficient in the ingredients that were used to make our electrodes. So potential improvements, our actual film did not incorporate the membrane, and that is a pretty important component, and you can see that from the graph below that I got from one of the papers. And the absorption is when you absorb the ions into the electrode, and then when you reverse the voltage, you get desorption. And you can see there's kind of a slope between the two stages. However, when you incorporate the membrane, there's no longer that slope, and it's more efficient because there's no opposite ions going into the electrodes. So that's one huge improvement that we could make. The other thing is Nafion is pretty expensive. That's also another way we can reduce the cost. It's a really good binder though. It's very stable, but its cost was really astronomical. It was $500 per 100 milliliters, which is very expensive. And there are alternative binders that we could experiment more with. More dense nickel foam, obviously. The more dense it is, the more the surface area. However, you don't want too much because you don't want too much water resistance. And another thing is the testing on the effect of aging on electronegativity. Our test was obviously short-term. We didn't really take into account the aging factor on the materials, especially for CNC. CNT, we predict that it would be stable, but for CNC, especially aging might take a toll on it. But overall, the project was a success as a first stage testing and going through the product. It was really successful. These are our acknowledgements, Professor Pruzé and Professor Vivek Maheshwari, and our references. And that concludes our presentation. Questions?
Yes.
I'm just curious, you did your tests in water, which is clean, but you're going to be processing water from the environment, which has bioburden. Do these technologies tend to experience fouling from bacteria or other organisms?
Yes, they do. Because most of the bacteria are negatively charged, so some of the bacteria actually gets absorbed inside your porous materials.
Yeah.
So we tested using NaCl solution, but they do actually do biofouling. And that's the main reason they actually use the opposite charges, because you can actually remove all the ions from things by just short-circuiting your materials if you do that. But they use negative because to try to remove most of the biofouling out of your porous materials.
Polymers you're using, do you know if they have any track record with biologicals? Some polymers really take up stuff.
Yeah, we haven't actually tested that.
Yeah, there's also a lot of the CDI units, the commercial units, they incorporate carbon filters as well. Like they take into account like bacteria and all those, so it's incorporated into the system as well. Especially because like if you're using CNTs, like you don't want that to get into the water system, so there are filters incorporated as well.
Yes.
So you functionize the carbon nanotubes with nitric acid?
Yes.
And anything further than that?
We refluxed it for 24 hours. That's all we did for the reflux.
Because you could eventually react those functional groups with a molecule like another polymer.
We followed the process in a paper that they used HNO3 and sulfuric acid together, which we did one test for, and we did one with the HNO3, and we found the HNO3 was giving us better results, so we went with the HNO3 alone. But
yes,
yeah.
But now you have functional groups that you could use to your advantage in order to add, say, another polymer that could interact with your substrate, which is viral.
Yeah.
Right, because maybe those nitrate groups that you have on the surface of the carbon nanotube might not be the best to interact with polyviral.
Okay.
Yeah, our functionalization was probably, it wasn't like the...
I think it was a main problem for us was the functionalization.
Especially for conductivity, I think that's definitely an improvement that we need to look into, is the functionalization process. Because we didn't, like from the SEM images, we weren't getting good binding, like it was evident.
It was our first time doing functionalization of CNTs when we did this. We don't have a lot of experience with it, but we just followed the steps in the paper. And I guess with more experience, you would know when to add. Like there was like steps that you had to add, the temperature control and all that stuff. Those all affect your functionalization, especially for the CNTs. So maybe as a future, the more experience we get, the higher efficiencies. Because I've read in a couple of papers they get up to 70 to 80% of functionalized materials. So, but we didn't get that much. We only got like 40 to 50% for the CNTs, and a lot lower than that for the CNCs. Yeah. Okay. Thank you.